educational satellite television programs.
Hello, teacher. Hello, students. Welcome to today's lesson on periodic motion. So far in this unit, we've discussed uniform circular motion and the importance of angular frequency. We have learned how to determine the displacement, velocity, and acceleration of an object oscillating with simple harmonic motion. Today, we will study forced oscillation and resonance. We will also learn how to distinguish between free and damped oscillation. If you are ready to begin, students, we will start the lesson. I would like to begin with an activity. Students, imagine that you are pushing a fellow classmate on a swing set. Sometimes it seems like only a gentle push is capable of pushing your friend very high. Other times, it takes a lot of work to cause even a small amount of change. Why do you think this is? Work with a partner to explain this phenomenon. Try to use the terms you have learned that relate to oscillation. You may begin, students.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, everyone. I am sure that you had some very interesting discussions. Keep your answers close at hand. And as the lesson progresses, you will find out if you were correct. When an object is displaced from its equilibrium position and allowed to oscillate freely without any external forces acting on it, it experiences free oscillation. During free oscillation, an object oscillates at its natural frequency. Forced oscillation occurs when a force of constant frequency acts on an oscillator. Such a force is called a periodic driving force. When an object experiences forced oscillation, it oscillates at the frequency of the periodic driving force rather than at its natural frequency. Let us use the swing set as an example. After its initial displacement, the swing oscillates freely. When you stand behind the swing and push, you are applying a periodic driving force to the swing. You must time your pushes carefully, because if you try to push the swing at the wrong frequency, it can be quite jarring. However, if you time your push just right, you will add your force to the swing's natural frequency. With only gentle pushes, you can quickly build up a large amplitude. Your friend might have to ask you to stop pushing if he or she goes too high. When the frequency of the periodic driving force is the same as the oscillator's natural frequency, energy is transferred easily into the oscillation. The amplitude of the oscillation becomes large, sometimes very large. This phenomenon is known as resonance. The natural frequency of the oscillator is often referred to as the resonant frequency. Students, have you ever heard of an opera singer breaking a wine glass with her voice? Every object has a natural resonance, even an object like a wine glass. If a singer can find the right pitch to match the frequency of the glass, this tone will induce oscillation in the glass. The amplitude of the oscillation will become greater and greater until the glass cannot withstand it and shatters. The glass itself must not be affected by damping. Damping forces are resistive, energy dissipating forces that oppose the motion of an oscillator by acting in the opposite direction to its velocity. Engraving or embossing a wineglass's surface provides a damping force because it alters the surface tension of the glass. Air resistance and friction are typical examples of damping forces. These forces are the reason why pendulums eventually stop swinging. The damping force is directly proportionate but opposite to the velocity, as we can see in this equation. Here, B is the damping coefficient and V is the velocity of the object. Both values are dependent on the medium providing the damping force. Although the amplitude of an oscillation will decay exponentially, it is important to note that the period of the oscillation does not change as the amplitude gets smaller. In these displacement time graphs, we can see the effect of different amounts of damping force. With light damping, there is a gradual decrease in amplitude. Heavier damping is slightly less gradual. Critical damping allows the oscillator to return to its equilibrium in the shortest amount of time possible. And finally, overdamping prevents oscillation entirely and only allows the oscillator to return slowly to its equilibrium position. Students, I would like you to work with a partner and make a list of at least 3 examples of damping forces in real life. Please write down your answers.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. I am sure that you came up with many examples. I will share some of my own. In a piano, small blocks called dampers drop onto the piano strings to stop the vibrations of the notes. In vehicles, shock absorbers act as dampers to dissipate kinetic energy. Many structures, such as bridges, contain dampers that help to absorb or reduce the oscillation caused by wind or other periodic driving forces. These are just a few examples, and I am sure that you will be interested in sharing your examples with the class after the lesson. In today's lesson, we learned the difference between free and forced oscillation. We learned about periodic driving forces and what happens when these forces are applied to a natural frequency. We also discussed resonance and damping and studied several examples of damping forces that we encounter every day. In our next lesson, we will study the energy transformation that occurs during simple harmonic motion. Until next time, thank you, teacher. Thank you, students.